Hi there, my name is Jason Leo, and today we're going to learn some quantum physics, and we're going to mainly focus on the Schrodinger's equation.
For centuries, people have been using the traditional Newton mechanics system to describe how objects move around the world, such as a ball, a race car, or even a spaceship. We use the law of motion, law of universal gravitation, and the law of conservation of momentum and energy to describe them. However, when we put our lens inside an atom or inside the realm of microscopic world, it turns out that our physics don't agree on what's happening inside. And these equations that we just discussed just doesn't work anymore.
Now, before we start, we need to understand a very important concept in quantum physics, which is wave-particle dualities. This suggests that for any given microscopic particle, it has the properties of a wave. Now, in case you may wonder, what are the properties of a wave and a particle? Some properties of a wave including that it has amplitude, frequency, and its own wavelength, whereas properties of a particle including that it has volume, density, and mass, and there is space between particles, and that every single particles are attracted to each other.
The concept of wave-particle duality was primarily being discovered through the double-slit experiment, where scientists analyzed the result from projecting light through two slits. However, this is not the topic of this video and will not further discuss it. What we have to know from this concept is that for every single microscopic particles, it can be treated as a wave, which means that for every particle, it has its own wavelengths. Now, how do we calculate the respective wavelengths for each particle? Well, it is determined by the Broglie hypothesis, which is proposed by famous physicist Louis Victor Duc de Broglie. Now, in this equation, wavelength is equal to h divided by p. In this equation, the left-hand side letter stands for wavelength, h stands for Planck's constant, and p stands for the momentum of the particle, which is equal to mass multiplied by velocity. Now, in case you do not remember what is a wavelength, it is the distance between two identical points on the wave pattern. From this hypothesis, we can know that wavelength is inversely proportional to mass, meaning that the higher the mass is, the smaller the wavelength is. With the idea of wavelengths in mind, let's now take a look at the actual Schrodinger's equation, which is this. Now I have to let you know that this is the time-independent form of the Schrodinger's equation, or we don't put account into the effect that time has on quantum systems. This part in the equation circled in blue indicates the kinetic energy of the particle, whereas this part circled in green indicates the potential energy of the particle. For every single microscopic particles, its total energy is equal to kinetic energy plus potential energy. Therefore, we can see this Schrodinger's equation as an energy equivalence. This part circled in red, the total energy part, is the part that we're trying to solve from this equation. And by solving that, we can derive the wave function, which is the ultimate goal of Schrodinger's equation. Firstly, let's take a deeper look at the left-hand side of this equation, the kinetic energy and potential energy of the particle.
Now, there are basically two forms of energy in our life. The first form is kinetic energy, which is the energy that objects or particles possess due to its motion. For example, a biker is riding a bike at a certain velocity towards a certain direction. Then both the bike and the biker possesses kinetic energy to the same direction as velocity. The amount of kinetic energy can be calculated by half mv squared. The second type of energy is potential energy, most commonly referred to gravitational potential energy in our life. However, for a particle
we refer to chemical energy. Now, what is chemical energy? Chemical energy is the energy stored in chemical bonds of particles. Now, unlike kinetic energy, the potential energy of particles exists in all particles or molecules. Well, a perfect example to illustrate the idea of conservation of energy is by analyzing the motion of a simple pendulum. When the pendulum stops briefly at the top of its swing, the amount of kinetic energy of the system is zero, and all the energy of the system is only in potential energy. And when the pendulum swings back down, the amount of potential energy is converted back to kinetic energy. However, at all times, the sum of potential energy and kinetic energy is a constant, which means energy is always being conserved. Well, let's then take a look at the right-hand side of this equation. The right-hand side term contains two parts, the capital English letter E and the capital Greek letter psi. The E here stands for the energy level allowed for a particle, whereas this psi stands for the wave function. Well, let's first take a look at the energy level allowed inside a particle. To understand the fact that particles can only have fixed energy levels, we need to first understand what's Planck Einstein relation. Now, this relation is built upon the fact that energy is being quantized. What does quantized mean? Well, basically all matters are quantized because they consist of particles that can't subdivide. A particle can be break down into consisting of certain amount of protons, neutrons, or electrons. Now, the idea is same during energy transfers. The amount of energy that were being transferred doesn't just go there at once. Instead, it transfers in small packets with certain amount of energy in it. And according to the fact that it is quantized, these packets is not subdividable. Now you may wonder how much energy is in one of these packets. Well, it is determined by the frequency of the object. Well, I'm sure everyone has heard of the term frequency before. Waves with shorter wavelengths has smaller frequency and vice versa. In scientific language, frequency is equal to 1 divided by wavelengths. Now, related this was the Broglie wavelengths that we mentioned earlier, we can say that frequency is proportional to mass, meaning that objects or particles with higher mass has higher frequency. Well, with the idea of frequency in mind, we can actually work out the relationship between the energy level allowed and frequency. Now, another equation that we're using here is called the mass-energy equivalence proposed by Albert Einstein. Now, in this equation, Albert Einstein states that energy is equal to mass multiplied by the square of speed of light. Now, what we have to know from this equivalence is that energy is proportional to mass. Well, since we now know that energy is proportional to mass and frequency is also proportional to mass, we can easily conclude that energy should be proportional to frequency. Well, that's basically what the Planck Einstein relation tells us. The Planck Einstein relation is given by energy is equal to Planck's constant multiplied by frequency. This is mainly being discovered by Max Planck based on the work of Albert Einstein. In this relation, the H term here is a constant. Now the E term here is the amount of energy in each packet during energy transfers. We can see that as frequency or mass increases, the amount of energy in each packet also increases, which corresponds with our earlier conclusion. Now we know what does this E means. Let's take a look at this psi, which is the wave function. However, before you get into it, we need to understand a very important concept. So you might have heard of the Schrodinger's cat before, where the cat is in a state of being both alive and dead. Well, the particles are basically the same. Now let me make this entire thing easier for you to understand using a daily example. Now say a kid you know is trying to convince his mom to buy him an ice cream. However, because it's winter and it's pretty cold, her mom is reluctant to buy him an ice cream. But this kid got a pretty good grade in school, and his mom kinda wants to praise him for that. Now remember, because we know this kid and his family, we're able to make predictions on what will his mom probably act. In this case, there is approximately 60% chance of rejecting, 30% chance of approving, and another 10% possibility of buying him another treat instead. However, unless we go talk to this kid and ask him what happened that day, we will never know for sure what happened that day. Therefore, the kid is in a superposition of having all the possible resolution at once, just like the Schrodinger's cat. Now similarly, in microscopic world, this idea is also applicable. And one easy example to show this is using the particle in a box model of an electron. An electron is being placed randomly inside a box with infinitely high wall, and we want to determine the position of the electron. The only thing we know is that the electron is 100% chance inside. However, unlike the prior example, we doesn't know this electron and therefore was unable to make these predictions based on our experience. And that's what the wave function tells us. The square of the wave function tells us the probability distribution of the particle inside that box and was determined by frequency. Now the general wave function solution of the one-dimensional particle in a box model looks like this. In this expression, L stands for the length of the box and N stands for all positive integers. As I mentioned earlier, the square of the wave function indicates the probability distribution of the particle at certain location in the box. And after knowing the general form of the solution, we can now graph it and see how does it looks like. In this graph, the two lines on the side, colored in blue and purple, represents the side of the box. In this case, the n in our expression is equal to 1, and by analyzing the graph, we can see that there is no possibility of the particle outside the box, which means this is a wave function that can describe this particle. However, if we change the n value to something that is not a positive integer, such as 1.3 in this case, by analyzing the graph, we can see that there are some possibility that the electron is outside the box, which is not true in this case because we know for sure that there's 100% chance that the electron is inside the box, which means that this wave function is not a solution to this model itself. And that's the reason why the n in the expression of the answer of the wave function can only be positive integers. This can also be easily proved during the calculation of the wave function solution, shown here. Now, from our analyzation, we can see that only certain wave function can describe this model, and that the wave function tells us the probability distribution of the particle at a certain location. However, before we observe, we'll never know for sure where the electron is, which means that the electron is in the superposition of all positive locations, and we call this the superposition of eigenstates. Furthermore, in this example, we can also see that energy is being quantized because since only certain wave functions are allowed to describe the system, only certain energy levels are allowed for this system, which means that some energy levels are allowed, whereas other energies are not allowed for particles in this system. Therefore, we can see that energy is being quantized, and only certain energy level is allowed in this system. Well, I'm sure some of you are still confused now. How can a particle be at a superposition of all possible locations before observation was made, right? Because there's only one particle, right? How can it be at multiple places? Well, this all has to do with the fact of observation. Now, once an observation is being made,
we had interaction with quantum systems, and this means that the wave properties of this particle has loose, and we can only find it at a fixed location. In scientific terms, this is being described as wave function collapse, where we no longer need to use wave function to describe where the particle is. Another short extended knowledge here that might be interesting is that observation in particles is one way where quantum systems evolve in time.
Wow, that is a lot of explanations. And congratulations, you now understand what the Schrodinger's equation is. Now, another question that you may consider right now is that what is the usage and applications of this equation? Well, actually, there's plenty of them.
Now, one of the most important applications of the Schrodinger's equation is chemistry, where solving specific Schrodinger's equation allow us to predict the outcome of chemical reactions. However, as we can see from the particle in a box model, these equations are really hard to solve, and currently our computer can only solve the Schrodinger's equation for hydrogen. However, as our computers continue to be developed, it is fair to believe that in future a lot of chemical problems can be tackled through solving Schrodinger's equation.
But hold on. This example is still in science field, right? Everyone knows chemistry and physics are related. What are the actual real-life applications of it? Well, to be honest, there's a lot. And a good example is the smartphone and computer industry. Well, in this industry, I will select an obvious example, which is semiconductors. As a lot of you may know, semiconductors are a crucial part of manufacturing many electronic devices. Well, how do we create a semiconductor? It has to do with the band structure of solid objects, which is fundamentally a quantum physics concept. And that by adding and combining different elements of different amounts, we can create different semiconductors with different conductivities that we can utilize them later. However, how do we know which element and what elements to add? Well, by solving equations such as the Schrodinger's equation and other quantum physics equations. Now, what will happen if we don't have this equation? Well, basically, every chip that we have right now will not work, and you can pretty much imagine what the world will be like if that actually happens. My name is Jason. Thank you for spending time exploring the beautiful physics world with me in this video.